Hello, welcome to our next set of notes. We are now working on math and visual arts. So last time we covered math and music, but now we're going to dive into visual arts. First off, we're going to talk about perspective. If you took drawing classes and you learned about perspective, you probably see how it is really closely connected with math. Perspective is the art of drawing objects on a 2D surface, so on your painting, on your paper, and giving an impression of the height, width, depth, and the relative positions. So this is where you're drawing something. You can tell that one object is taller than the other, or one object is further away than the other. You have to be very intentional to create that kind of effect. So their desire to create landscapes, paint landscapes with three-dimensional realism, they wanted things to actually look like they do in the real world. Renaissance painters had to develop an understanding of perspective. They could capture the depth and the volume on their two-dimensional canvas. So one of the first people to really look at this was Filippo Brunelleschi. I'm going to apologize now for all the pronunciations. I'm not a historian, so I haven't studied how to pronounce all these names, so I'm doing my best. But Brunelleschi was an Italian architect, mathematician, designer, goldsmith, sculptor. He had lots of jobs, lots of different things he studied and was into. But he developed a precise system for linear perspective. He was trying to draw things as they appeared in real life, but doing that on a 2D canvas. And so he tried different things to make this work. And he had this interesting experiment where he actually poked a hole through his canvas, a really small hole, but nothing you could see through, but in the picture. And he would paint his picture, and then he would look through the back of the canvas at whatever he's painting, and he would hold up a mirror, and he could see his canvas, and he would move the mirror to the side or move it away, and you could see, what he was painting would be there. And so he could see how well he did capturing that. So this is before you had photographs and before you had other ways to check and see how good your painting was. You could try some side by side, but this way you could really quickly, look at the difference between the two. You could just move the mirror out of the way real fast and see the difference and see if it was the same. So this kind of picture over here shows what he's doing, how he's looking through the back of the canvas and has a mirror, and he's looking at this building over here, and then he moved this mirror off to the side real quick, and he'd be able to see instead of his canvas the actual building, and he could see any differences. Another person that really helped develop the idea of perspective and drawing this way was Leon Alberti. He was an Italian architecture, author, mathematician. Notice both of these guys were into mathematics. Back then, if you had the money and the resources to study and be studious, you usually studied lots of different fields. So yeah, both of these studied mathematics, as well as art and architecture and all that stuff. He's famous for writing a series of books, one of them which was the De Pictura. In English, that would come translated as On Painting. And it serves as a guide to employing perspective, and actually influenced a lot of other really well-known Renaissance artists, people like Donatello, Ghiberti, Botticelli, Ghirlandaio, and Leonardo da Vinci. So these are names that we've all heard of. Da Vinci's hugely famous, and they were influenced by Alberti's writings. He actually wrote about how to draw in this way, how to use perspective and get more realistic pictures. All right, let's talk about how perspective works. One of the important parts of perspective is called the principal vanishing point. So we have a hallway with the vase in it, and we're looking from the side view and through this hallway. Now, if we wanted to draw this hallway scene on a 2D canvas, one thing you'd notice when we go to draw it is that the corners of the hallway, so the edges of the hallway, instead of just going forever and never getting close to each other like they do in real life, they actually, the end corners of this hallway look like they're meeting up at some point. That point is called the principal vanishing point, P. So it's a central point where they would meet. There would be a central vanishing point called the principal vanishing point, P. So the first principle of perspective, one of the really important, most important rules of perspective, is that all lines parallel in the scene, so like the hallway corners are parallel, they would normally not, in real life, they would never touch, and perpendicular to our canvas. So if we were drawing from this side, our canvas would be right here. In the canvas, these lines would be perpendicular to that canvas, they must intersect at the principal vanishing point. So parallel, all lines that are parallel in the scene and perpendicular to the canvas, intersect at the principal vanishing point. That's the big first principle. So like right here, now we're looking at like the canvas. If you drew this hallway scene, you'd see these corner lines over here, the hallway corners. They all, if you extend them, would look like they're going to meet at this central point. So any set of lines that are parallel to each other but perpendicular to the canvas, they make a nice right angle with our canvas, and they're parallel to each other, would do this. In fact, these middle lines over here are going to do the same thing. If you extend them, they would all cross at that principal vanishing point. So that's going to be true for any set of parallel lines. So if you have like railroad tracks, or if you had a road, what happens is it will vanish, and it'll get narrower and narrower as it gets closer to that vanishing point P. Now that's what happens with lines that are parallel to each other and perpendicular to the canvas. However, what will happen to lines that are parallel with each other but not parallel or perpendicular to the canvas? So what happens? So lines that are parallel with each other but not parallel or perpendicular to the canvas. So what lines will we be talking about? Well, we actually be talking about lines like this one. So if you draw a diagonal down these tiles here, these lines, oops, they're drawn, hopefully good like that. These lines are parallel to each other. You can see how if you run down the diagonals, if you look at this hallway and think about like, okay, how that works. These lines would be parallel to each other, but they're not at a nice right angle with the canvas. They're kind of a slant with the canvas. Well, you notice in these case, these lines actually do meet up at a point. So even though they're not meeting at the principal vanishing point, they're going to meet at other vanishing points. So this is still a vanishing point. It's just not the principal vanishing point. So if you have a set of parallel lines on your picture, they are going to, as you get further away from the front of your picture, they're going to get closer and closer together. Eventually, they're going to meet up at some point. And that happens for those ones. It actually happens this direction as well. So these lines go in the other diagonal. They meet up over here on this side. So we have those ones as well meet up at the other vanishing point. That's on the picture. It depends on where things are pointed towards. So, where these parallel lines are kind of pointed out that direction, and they get closer and closer as they meet to that point P. So they meet at some other vanishing point. I had to say that they're not perpendicular to the canvas or parallel to the canvas, because lines that are parallel to the canvas would be like these horizontal lines here. They actually don't meet at some point out in the distance, but what you will notice is that these lines, like the horizontal lines running across these tiles here, do get closer together the further you get away. So if you have this hallway extended on forever, you can see that the lines would get closer and closer together until you basically couldn't tell them apart all the way off at the distance. Okay, from this picture, so the picture we were looking at, and then this one's kind of similar. It's got the same grid situation with the principal vanishing point P, and some other vanishing points for the diagonals. We can see that the principal vanishing point and the vanishing points all lie on the same line. They're all on this line that's kind of connecting all these dots, and note that all the vanishing points lie on this the line that we call the horizon line. So this horizon line is where you have all your vanishing points, your distance points, your vanishing points, your principal vanishing point. They're all going to be on this horizon line. This is going to be the line that basically separates stuff that's like on the ground from the sky. If you're drawing outdoors, you'd put the sky up here, you'd put the grass down here. You could do similar things inside buildings, but it'd just be a little different, but that's the idea. The vanishing point of that horizon line, where you separate the sky and the ground, that's where the vanishing point is always going to be. Now, these artists studied these principles of perspective, and they used them in their artistic works. So many great artists, lots of great artists, used perspective. It's still something people use today. In The Last Supper, Leonardo da Vinci used this principal vanishing point, he placed it directly behind Christ. This Last Supper is representing the scene with Christ and his disciples. And he purposely put it right behind Christ. That's where the principal vanishing point is. You can see all the parallel lines, that are in the ceiling and, kind of along the walls and stuff. They all would vanish to about the point around here, and it naturally centers your eye and focuses the piece. So you used perspective and placed Christ right in front of the principal vanishing point, so everything about the room would actually draw you to that point. And there's lots of different artists, and they do it in different ways, but perspective is a really important aspect of art. Another way we see perspective is actually some artists that distorted perspective. They actually used it intentionally in a way where it doesn't work like you'd expect. So here, M.C. Escher, who's a pretty famous mathematical artist, we'll mention him a couple times today, he was actually showing the difference kind of between the 3D world and the 2D world. So he drew this picture, and you can see there's a water mill, right here where the water's falling down, and it's running this mill, and then it runs back behind the mill, and then it runs through this path, and all of a sudden it's back up above that water mill. So it's doing this impossible journey because it can't flow uphill to start over and do it again. But it looks like it should work. If you just casually glance at it and don't look at the details, he's using perspective. He's making things appear like they're correct. But this shape is not possible in a 3D world. You couldn't have this structure the way it is. It actually employs what's called a Penrose triangle. And these triangles are basically an impossible object. A triangle can't be connected in this way in the 3D world. It looks fine in 2D, it looks like a regular triangle. But in the 3D, it doesn't really quite work. There's Penrose triangles. He had some other shapes. He included some polyhedra from mathematics as well, because he was definitely inspired by mathematics. But yeah, using this impossible situation. So that's waterfall, lithograph he did in 1961. Here's another lithograph. This is called Relativity. He did, even earlier actually, in 1953. And this one, he followed the law of perspective. So if you look at individual pieces, it kind of makes sense. There's the stairs, people climbing up them, or they're going down the stairs. But if you look at it, you start saying, well, everybody's going different ways. It doesn't make sense. What actually happened is he basically created 3 different setups for gravity. He's got some people where gravity's up and down. So like down here, you can see like gravity's up and down. Over here, gravity's going this way. And so here's people sitting down and standing. Gravity goes this direction. Same for like this person, And then he's got another form of gravity going this direction. So these guys are all sitting on gravity going that way. So the gravities are working in different directions. There's different sources of gravity. And they're doing things like having this person walk on one side of the stairs and this person walk on a different side of the stairs. So he's using perspective to create a scene that, at first glance seems like it's realistic, but then you start noticing all the things that are wrong with it. We don't have multiple sources of gravity in one room. You can't follow one law for one person, one law for a different one. Things like that. A person walk down stairs that seem to go up, and also someone else is walking downstairs that are a different way. So he's playing with that, and he's distorting our view of reality, and it clashes with what we expect. So it has a profound effect because of that. Okay. Next thing we want to talk about is symmetry. So we're not going to spend a lot of time, you'll notice on the homework and stuff with perspective. It's something very important to mathematics, but unless we're going to get really into an art class and start doing a lot of drawing, which we're not quite going to, we're not going to do a lot of math problems with it, but we'll definitely do some problems on symmetry. So symmetry has lots of different meanings, lots of ways to define symmetry. One example, in the Last Supper, there's a symmetry because the disciples on both sides of Jesus are placed in 4 groups of 3 with 2 groups on each side. So we have group here, group here, group here, group here. So it's split 2 groups with 3. And symmetrical because it puts Christ in the center. Again, he's leading for that focus, that sense of focus on Christ in the middle. And then the spacing, and so he's used that to create this kind of symmetry between the 2 sides. Another place we think about symmetry, we think about the human body. So the human body is symmetrical because if you draw a vertical line right through the middle, if I take a ruler and just put it right through the middle, the 2 halves match, right? You've got the 2 same halves, especially if you get the ruler nicely centered. But we've got our arm on either side, our leg on either side. You know, the chest is the two halves, the face, we've got two eyes, and, you know, two ears and all that. So there's this, you know, nice line we can draw right through the middle that makes that symmetry. This is Vitruvian Man by Da Vinci. It's, you know, famous for showing what supposedly the perfect archetype for human body and stuff. So something pretty ubiquitous. You've probably seen that before. When we think about symmetry in mathematics, a symmetry is a property that remains unchanged under certain operations, things like reflection, rotation, or translation. So it's something that, you know, if you do a reflection, rotation, or translation, you'll notice that nothing's changed because there's symmetry. Those two things match. So we'll talk about all three types of symmetry. First off, let's talk about reflection symmetry. So reflection symmetry says an object remains unchanged when it's reflected across a straight line. This line can be vertical or horizontal, as we show below here. So like here we have these vertical lines where you can draw the two halves. The A is not quite centered, but the M you can see nicely centered, and the two halves match. The U, the two sides match. The W, the two sides match. And then you have horizontal lines, so you can see like E, B, C, and D, they fold up and down. So you should be able to like look at the top and bottom half, and they look exactly the same. So these would be lines of reflection symmetry. And so we can find these ourselves. So we can look at a shape and decide, okay, where's the line where I could draw that it would get that nice reflection symmetry. Well, here with the star, I think the most clear one is this straight up and down line. So we have, my pen doesn't like to draw in the middle, but this straight up and down, so we can fold it horizontally. We have a vertical line we can fold over, but it's actually not the only one, because you can actually, if you look at the star this way, and you see, well, now this is actually kind of a straight up and down line. That's actually another reflection line. If you look at it this way, there's another line right here where you can go straight up and down. And there's one more if you turn it this way. You can see this one. Fold straight up and down. So we actually have, and this one. I missed one. I said one more, but there's one more. You know, let me turn it enough on you, but there you go. You can kind of see it. You don't have to turn it to see it, but I think it kind of helps to see that we're doing that same fold, basically. With this star, we end up with actually every single point gives us a line. If you notice that you have a point to the opposite, like indent. And so here we actually have 1, 2, 3, 4, 5 reflection lines. Some have less, some have more. You know, if I try to do this plus sign here, I can fold straight up and down, just like that other one. But I can also fold straight across. You can see how the top and bottom half will match there. But that's not it. It's actually more, because you could cross diagonally. So I can see how, like this, the two sides still match, right? I have my side over here, side over here. And I could actually do that this way as well, because now the top and the bottom sides match. So this one actually has 1, 2, 3, 4 lines. So this is a few less. It has 4 reflection lines. The lightning bolt down here, none, right? There are no reflection lines. There's not a spot where I could draw a line that goes through the shape that it matches. I mean, you can't even draw one next to the shape. There's no line I could draw where two halves would match. If I try and go down this way, well, these sides and these sides don't line up, don't match. So this one would have none. So it's possible, definitely, to draw shapes with no reflection lines. Some have fewer. You know, this one here, you can see that if you draw a line right through the middle of this slash, that would be one. There's actually one more, maybe a little less obvious, is this one right here. You can draw one this way and see that. If you need help trying to figure this out, if you have a hand mirror, a little mirror you can use, you can actually kind of line it up like this and then look at it and then pull it away. And sometimes it'll help. You can use your phone to do that. You know, if you have your phone and you like turn the camera on, some people use that. But basically, yeah, you should be able to draw a line across, and the two sides should match. This one has 2 reflection lines. That's a reflection symmetry. Anytime you can look for a spot where you can fold it in half, and the two sides will match. Next, we have rotation symmetry. So any object where you remains unchanged when it's rotated to some angle less than 360. Note that it has to be less than 360 because if you rotate an object a full 360, that's just when you take the object and rotate it all the way around back to the start. So every object has 360 rotation because you just went back to where you started. So we have to do some amount less than 360. So like this first shape, if we just rotate it upside down, well now it still looks like the exact shape because it's just upside down. So this one has a 180 degree rotation where you can rotate half of the 360, 180. So this would be, one rotation. So that's like, here that'd be 180 degree. This one's not so obvious for the degrees, but you can see here that if I rotate it, so instead of this being the top, now I have this part as the top. Now it's the same shape, it's the same star, so that works. But I could keep going, right? I could actually put any of these points in the top, and each time I'm going to get, a different position that works. So these all would work. So these would all be, spots. So I'd rotate, that far each time. Here, I want to rotate this one. I'm just going to rotate one position to the next arrow being on top. So I went from this one being on top to this one being on top. Rotate it again. Put this one on top. So I actually have 3 spots I could stop. So rotation here would go from here to here, from here to here. So rotation, I should be able to take it and turn it. If you had something like a book or a picture on a screen, one thing you can do is you can actually just pull out your cell phone and take a picture of the object and then rotate it. As long as you keep your phone kind of flat, that's what you can kind of, or lock that, so the rotation on your screen. But you can kind of use that to help with trying to figure out rotation when you're doing homework and stuff. Okay, let's try and draw some shapes that have one, not the other. So first, let's do at least one reflection, but no rotation. So I want something that can fold in half but doesn't rotate. I think one of the easy things to use is letters, and the easy letter that works for this is A. So A definitely has a reflection. It was one of our lists on the previous page. We saw that the line goes right down the middle, but it doesn't matter if you rotate it anything less than 360, it's not going to be the same capital letter A. It's not until you get all the way back to the beginning, 360 degrees, that you're still, and you're an A again. So that one would have reflection, but does not have any rotation. Another example would be E. E would be one that works because capital E has another reflection. You can reflect it horizontally, the top and the bottom reflect, but if I try and rotate that at all, I'm not going to have an E. This would be pointing in the wrong direction until I get back to my original position. So these are a couple examples of things that reflect, but they don't rotate. Let's go the other way. So what if I want to find at least one rotation and no reflection? This one's a little weird to think about because it's hard not to draw shapes that have reflection. One thing that helps is to draw shapes with curves. So something like S, it will rotate, because you rotate upside down, it's back to being an S again, but there are no reflection lines. There's nowhere you can draw a line that it will reflect. So this one will have no reflections. Shapes like the arrows and the recycling sign, stuff like this works really well. Because if you have things with curves in a sense like that, those things kind of tend to work. So like that's why S kind of works with curves. You could do something like to draw a triangle I want, and then just put like curves on it. So go like this on the tops of the corner of each one. So just each corner have that same kind of curve. And now there's no reflection line, because anytime you try to draw a line, it won't work. But now I could rotate it and just put that each corner on the top, and because they all have that same curve, it actually now has no reflection symmetries, it just has rotation, no reflections. So no matter where you try to draw your line, you're going to make something where the two sides don't match. Okay, the last type of symmetry we talked about, before I get to that, I should talk about how to get the angle of rotation. So I mentioned the 180 on this shape. I said, okay, this shape has a 180 degree So they said, well, you're just doing half a turn, 180. But these other angles, these other shapes also have angles that you could also rotate. So how do we find that? To calculate the angle of rotation, that's like how much you have to turn before you get the same shape you started with. The angle of rotation, you're going to divide 360 by the number of stopping points. Don't forget to include the starting point. That's how we can calculate the angle of rotation. That's how many degrees object needs to be rotated to match the original shape. So for example, I've got this triangle here, and it's got the starting point here. If I rotate that to here, that would be one rotation. I could rotate here to the next starting point. These would be the 3 points I could stop at. So I would take 360, and I divide it by 3, and I get 120 degrees. So this rotation, one rotation like this would be 120 degrees. If I do it twice, I'd end up here, because 120 equals 120. If I do it 3 times, I'm back to where I started with it, with a full circle. So 3 times 120 more would give you 360. So this one I could rotate it 120. I could rotate it 240, because that's doing 2 of them. But I'm not going to write down 360, because like we said, we're only worried about rotations that are less than 360. So these would be the angles I could rotate that. You could do more, right? You could do 360, you could do 480, you could do 600. Those are just adding 120 over and over again. And those would be other angles you could rotate it, but really at that point you're just spinning this triangle around in circles a bunch of times. So the ones we're really going to care about are these two, because these are the ones that you can get before you get to 360. Let's try this shape. This one, same idea. We look at the stopping points, so like our starting point, and if I rotate, I could rotate to here, rotate over here, rotate over here. So I end up with like 4 points where I can stop, right? I can't stop halfway through. I can't be like, oh, that's the same shape. I have to stop when one of those points is on top, because then it looks like the original shape. So then I have 4 stopping points. So I would take my 360 and divide it by 4, one for each stopping point. So that would give me this angle here, how much I'm going to turn. And in this case, it ends up being a 90-degree angle. So this is 90 degrees. Yeah, that makes sense. If you do 90-degree angle, you're turning just a quarter turn, that's 90 degrees. And so I could keep doing 90s to get these ones until I get back to 360. So 90 would work, 90 degrees. But so would, if I do another 90, I would get 180. If I do another 90, I get 270. And if I do one more 90, I'm back at 360, right? Now 270 plus 90 is 360. So these would be the angles I would care about. Again, once I get to 360, I don't really care about that, because 360 is just full circle. We're back where we started. So that's why we have to divide by 4, even though we only end up with 3 answers, because we're not really worried about the 360 answer. So that's what we're talking about. We talk about the angle of rotation, how much the rotation has to be to get back to that starting point. And it's all based on how many points do you end up that you can stop at. And the shape gives you that. So like back here when I had this 5-point star, 1, 2, 3, 4, 5 points, I would divide 360 by 5. Or with this 3 arrows, I would have 3 stopping points. I'd divide 360 by 3 to get the angles. Okay, sorry, I forgot about the page. Now we can talk about translations. So the last type of symmetry we have is what's called translation symmetry. The translation symmetry is when you take an object and you just shift it over and over and over again. A lot of traditional paintings and pictures, textile stuff have been made using translations where you just take a shape and just shift it over, and shift it over, and shift it over, and shift it over. So we're just going this way over and again. And that would be a translation. Here you can go to the right, you can go left, you can go up, you can go down diagonal. All those are fine, but you're just using a pattern. You're taking a shape, and then there's some kind of spot where you just repeat the shape. And then you repeat the shape, and you can just shift it to the side. In these cases, it's like left to right, but you can also do this diagonally, up and down, all kinds of things. Same thing down here, you can kind of cut a point and say, okay, this shape would move far enough over. That's right there. Move far enough over. There it is. Move far enough over. Here it is. So let's actually do this. We're going to take the capital letter B, and we're going to make 2 different patterns. All the ones up here are going just straight across. Let's do one that goes diagonally. So let's take a letter B and just shift it up. So we're going to put another letter B here, and we can keep going. We're going to shift diagonally, I should say, up to the right. My B's are not perfect because they're hand-drawn, but you get the idea. It's kind of like the feet. You just get repeated over and over and over again. There's no rule that says the letter has to be shifted past the other B. So if you want to do one where you like start with a B and you shift it where it's like just over top, and shift it just over top, shift it just, So now this is still a translation because I'm taking the same B, I'm shifting it over. In fact, you can kind of look at a little piece here and say if you shift it over and over again, you get the whole B. You could space them out. So if I wanted to do B's with space, I could do like that. Again, my B's are not perfect, so yeah, we know that they don't all look exactly right. But here I actually gave a couple different translations. So each one of these is a translation setup just using letter B. Now these are only just using translations, so I'm just shifting. Let's do one where I actually use both. Let's do both translations and reflections. I'm going to use the capital letter E this time, just to make it a little different. So I'm going to start with E, but what I'm going to do is I'm going to take this E, I'm going to reflect it horizontally. So I'm going to take this and reflect it and get an E going that way. And reflect it, get an E going this way. Now I'm shifting it over and reflecting it. So shifting and reflecting. Oh, I went the wrong way. That's supposed to be here. This is hand drawn. Mistakes were made. Okay, and then I go the other way. And so here I mostly using, I keep on put that E on the wrong side. It's hard to go backwards with these. I'll draw a few without talking. Maybe I'll want some of them. But yeah, so now I'm reflecting it. You could even have, I guess this one mostly it's just reflections. You could have one where you reflect and shift. So I have something like E here, and then have like E going the other way. So I reflect it and shift it down. And I can reflect it and shift it up. So this one kind of does a little bit more of both reflections and shifts. You couldn't just reflect to get the shape, but I have to reflect and shift. Here I go with my E's on the wrong side again. Okay. Draw a few without mistakes, hopefully. And there's lots of ways to do this. This is just one example, but here I'm using both a reflect and then a shift. So this is both. This one you could kind of argue maybe it's just reflections. This one had to use both reflections and translations. A lot of people call that a glide reflection when you reflect and shift. You make a pattern with that. It's called glide reflection. Okay. Now we talk about translations. One of the cool things you can do is use these translations, symmetries, and art. So artists have been employing symmetries a long time, since prehistoric times. Indigenous peoples created textiles, pottery, stuff like that with reflections and translations and those kinds of things. So those are common. I actually went to a math conference last week, and then someone was doing that. They did an analysis of the different types of translations, reflections, rotations on indigenous textiles, and that's something that's real well known. Another thing is that more modern artists, here I'm looking at 1800s and early 1900s, also employed types of symmetries in their art. They're a very powerful tool to create a strong visual influence. So this is The Vision of Empyrean by Gustave Doré. Again, sorry about pronunciations. So he's a French printmaker known for making wood graving illustrations. So he would carve out a wood block and then put ink on it and print it. That's how he made his illustrations like this. You can imagine trying to carve all the details he has on here and then stamp it and all that. And here, this is an illustration. He's really known for doing illustrations of the Vulgate Bible and for Dante's Divine Comedy. This scene is actually from Paradiso, the third part of the Divine Comedy, where Dante is in heaven. The Empyrean is actually in the book The Highest Heaven, which contains the essence of God. So this scene is supposed to be pretty dramatic because this is where he's observing the essence of God in the highest heaven in Paradiso. So they've used symmetry here. You can see how there's like rotational symmetry, except for the people on the bottom. This big circle has this kind of sense of rotation where you can almost spiral around as you go into it, and really draws you into the middle and focuses your effect. And it's because you use this sense of like rotational symmetry, where there's kind of this rotational pattern to it. So you put that symmetry in there, and it really just draws you in. Another example here, this is Supernovae. That's on canvas by Victor Vasarely. I'm not sure. He's a Hungarian-French artist known as the grandfather or leader of the opt art movement. So it's a visual art that uses optical illusions. So the idea was the pieces explore, geometry, perception, motion, how these things work. and it should visually like alter as you move. So this idea, when it was hanging up on the wall, you would walk by it and it would look different from different angles. I'm probably not going to get that effect as much with my printed paper on your webcam, on all this stuff, but that's in person. One thing that really blows my mind is my wife is an artist, and so talking with her and stuff, one thing I think as a layman I would never realize, but when you're working with like oil paint and stuff, and you're doing colors like a solid color shape and stuff, one thing that's really hard to do is get a nicely, really even finished coat, and also it's very hard to get nice straight lines. So when you make something like this, it might not look like big a deal, especially now with our modern tools where you could like create a program on your computer that would pretty easily draw squares and stuff. But he had to draw each one of these squares by hand, get all these nice straight lines so that the effects work, and he had to get nice even coating so that the squares all look the same. It just blows my mind, the amount of effort and technical skill to do something like this. But because he did that, he took the time and he did that. Now when he deviates and does things like having his circles here go from small to big as you go to the right, those little circles get bigger and bigger as you go across, or having like these squares more filled in and those squares less filled in. And it creates this really dramatic effect, and then it gives the optical illusion power to this piece. That's all because he's using, symmetries, but he's also using like kind of the lack of symmetries, the non-symmetry, the symmetries that exist, but then also the non-symmetry. And what's what creates this really powerful visual effect. Okay, last thing I want to talk about today is tilings. So tiling is when you have some area like floor, wall, or ceiling, and you cover it with repeated geometrical shapes. We call it tiling or a tessellation. Those are both kind of interchangeable names for the same thing. In mathematics, we specifically refers to an arrangement of polygons used to fill a two-dimensional plane. The polygons are these shapes that have a number of sides. They are closed, which means they're connected. There's no holes or gaps in the polygon. We typically think of regular polygons, and that's what we have down here. So these are regular polygons, nice regular triangles, squares, and hexagons. Regulars mean polygons are polygons where all the sides are the same. So tiling uses polygons. So it's an arrangement of polygons, fills a two-dimensional plane, and there has to be no spaces between the polygons and no gaps between the polygons. So I can't have like a little bit of gap. So here you could see you could fill it perfectly with a triangle. We just didn't keep going because you have to go forever, but you can see no matter where you look, there's always room for another triangle. Same thing here, you could put a new square on a new part, or there's a new hexagon space. These are the three simple examples of tilings, which use repetition of regular polygons, and they are triangles, squares, and hexagons. This is why when you go like to the house supply store and you want to buy, tile to put in your backsplash in your kitchen, if you want tile that just uses one shape, these are your choices. These are the three that work. In fact, there's actually been proven that these three regular polygons are the only ones that will make a tessellation. So if you try and buy something with octagons or pentagons, it ain't going to work. It's not going to cover your backsplash without gaps. They'd have to. You can do something with octagons, but you have to use other shapes as well. It wouldn't be just that one shape. So below, this is actually an illustration of why pentagons doesn't work. So pentagon cannot be used because when you go in, with the pentagon, the corner pieces here end up being 108 degrees. On regular shapes like this, all the corners are the same size. And for a pentagon, this corner is 108 degrees. And if you add up three pentagons, you end up with about 324 degrees, which is about 36 short of a full 360. And in order to get a full circle, in order to get a tiling, you have to have every corner have a full circle. In fact, if you look up here, at every corner, every one of these corners, they actually have a full circle worth of degrees. So like these guys have 90s, and 90s, 4 90s gives us 360. Triangles, actually, regular triangles have 60-degree corners. So when I do 6, 1, 2, 3, 4, 5, 6 of those times 6, you get 360. And these hexagons actually have 120 degrees. So these guys are 120 degrees. And 3 of those, so times 3, gives me 360. And that's actually why these are the only 3 that work, is because there are only 3 regular polygons whose corners will add up to 360 degrees. Anything like a pentagon doesn't quite make it. It's not quite as big as a hexagon, not quite as small as a square, 108's in between. and it doesn't divide 360, 108 doesn't go to 360. Anything bigger than a hexagon, so like septagon, octagon, stuff like that, what happens is the angles get bigger and bigger as you go, and they get so big they're just not going to fit into 360. So that's why you can't do anything bigger than a hexagon. Hexagon's the biggest you can get, and even pentagons don't work because they just don't divide 360 evenly. So only 3 regular tilings are triangles, squares, and hexagons. Now, again, this is if you just use one shape. So what people have done in the past is said, well, just mix together multiple shapes, right? Because if just one shape doesn't work, we'll mix together a few. So you can actually use, if you use more than one type of regular polygon, then there's lots and lots of options. So you can see it gives tons of options. So here they have hexagons and triangles. Here they got squares, triangles, and hexagons. Here we're actually to bigger shapes, right? So these are actually octagons with squares, so octagons and squares. Triangles and squares, I've got triangles and hexagons. These ones actually have bigger sides. So if you look at this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. These are called dodecagons. So dodecagons, squares, and hexagons. We've got squares and triangles. How many is this one? It's 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. That's a dodecagon as well, with triangles. So lots of ways to do it if you allow multiple shapes. So one way people get by. That's why if you go and look at tiles and stuff at the hardware supply store, a lot of them will have more than one shape because it gives them more options for what they can make. Now, if we ditch the regular requirement, if we ditch the fact that all the shapes have to have the lengths of the sides all be the same, then we can make what are called irregular polygons. So all the sides can be different lengths. There's no requirement they have to be the same lengths. We're still using the same shape over and over again, but sides on the shape are going to be different. So like if you look at this shape here, you can see there's a little tiny piece here, and then there's a longer piece here, and those are definitely not the same piece. This piece is probably longer than that piece. It's longer than that piece. So the different sides are different lengths. So they use this one polygon and it made a shape. It's just not a regular polygon. So it's got irregular sides. Same thing over here. You can look at this shape. It's got some long sides, it's got some short sides, it's got some medium sides. So it's irregular. It's not all the same side lengths, and it gives a whole bunch of options. Basically, the reason why irregular polygons can give us so many different tessellations, why there's so many different ones that work, is because now that they have all these different lengths of sides, they're going to have different angles, so they have more ways to add up to 360. It's not like the regular shapes where you just had one type of corner with one measurement, and you have to have that one add up to 360. Now I have corners here, and I have corners here, and I have corners here, and I have all these different corners, and so I can match up those different corners and get to 360 with different corners mashed together. So there's more ways to add to 360. That's why irregular tilings gives you lots of options. Artists have employed tilings. One of the biggest uses of tilings is actually the Muslim culture and their architecture, because traditionally they try not to depict actual life, animals, people, that kind of stuff. Part of their belief system, God is created, the creator, and the artist is not a creator. So instead, they actually did a lot of patterns and tilings, geometric shapes, because then they could make something really interesting visually, but not break that belief of not representing life in their art. Well, it inspired lots of other artists, including one of the most famous artists. We already mentioned him, MC Escher. He's really famous for his tessellations. So he actually took shapes, irregular shapes, not the typical hexagons and triangles and squares, but actually made irregular shapes look like animals and people, plants, and created tessellations with those. So he drew tons and tons of these. He had books full of tessellations. So here he did one with geese, so you can see that like white geese shape. You see the blue geese are actually the same shape, it's just going the other direction. So you could take this one and just flip it around, kind of flip it over. But you could just put in the white sheep and the blue geese, could be kind of the negative space. So a lot of times we'll just consider this a translation where you just shift it over and over again, and then the blue space is just the negative space. Same thing over here, we have the same horseman, over and over again, and then the brown space is actually negative space, but it's actually the same horseman if you look, because you have the same horseman, it's in that same shape. So again, these ones we would consider translations. So they were created using just translations. It's okay that, technically this horse is facing a different way than that horse, because that's kind of the negative space. But if you just look at the one color of horse over and over again, you can put that in there and make the whole space. Pick one color of goose and you can fill the whole space. So you did those with translations. Below, he's got a couple where he didn't just use translations for sure. So like this one, the lizards, you'll notice the lizards are facing all different directions. They've been rotated, so this one needs rotations. He didn't actually, I think, name these pieces because they're mostly drawings for like his own personal use for like when he wanted to do something later, just develop the design. So these don't have really labels; they're just like tessellations, it's, you know, different like, label numbers maybe. But yeah, this set of lizards, it's a rotation, so you can kind of see how this face is looking up, and then you can rotate it, and that'll look down. So if you take it, rotate it around where the arm is, you can get it to that position. You can rotate it and get it over to this position. You know, so they all just are rotated versions. Over here, he's got this dog. This one, you'll notice we have black dogs and white dogs. So if I look at just the white dogs, you can see if you have to be flipped over, it's kind of like that glide reflection. So like flipped and then shifted into a spot. So reflected and translation. So some artwork, some tessellations, you need both. You can't just use translations. So here, to get this white dog to here, you can't just shift it because it got reflected as well. Again, the black space is kind of a negative space. So I'm going to just look at the whites mostly here. But you could even get the black ones. If you just allow reflection, you can reflect the white one down here. You know, color is not necessarily super important. But when you're making art, coloring is, you know, it gives it more visual interest. If you're just trying to tile the plane like a mathematician would, we wouldn't be so much worried about color, but it's really worried about like positioning. How do we get there? You know, is it the ones where we can just like translate all day long, or is it ones where we have to like, rotate, or ones where we have to reflect? Okay, one really cool thing. So eventually, people were studying these tessellations, these tilings of the plane. And all the ones we've looked at so far, they figured out, well, you can find a big enough chunk, and you can just sit there and just translate that chunk. So if I look at like that dog one, I say you can't just take the one dog and like make the whole space. But if you get a set of dogs, so you get like this black dog, white dog, black dog, you get like a piece like that, then that piece is big enough. Now you can just translate it, go up, right, down, left, and you can fill the whole space. Same thing with this lizard thing. So it's like right now it's really complicated, but if you got a big enough set of lizards, you know, some black, white, and red lizards, you get a big enough piece, you could just start doing translations and just slide and fill the whole space. And that's going to be true for all the things we've seen so far. They're called periodic. So periodic means that the tiling can be translated, you know, the width of some tile, and the result you get is the same tiling. But you have to find a big enough piece. A lot of times that doesn't mean, you know, you just take one single dog or one single like lizard. But a lot of times you have to take a big enough piece and do it. Well, more recently, mathematicians have studied the idea of aperiodic tiling. So this is a tiling that doesn't repeat through translations. There's no piece you can find that's big enough that you can sit there and just translate left, right, up, down, and get the whole tiling. Now, back in 1964, not that long ago in math world, right? That's pretty recent, 1964. Robert Berger actually came up with a set of 20,000 tiles. His PhD teacher had been studying this idea of aperiodic tiling, and Berger actually managed to find a set of 20,000 tiles that were aperiodic. When they say aperiodic, that doesn't mean just that he made an aperiodic tiling. It actually means that these set of tiles could only make aperiodic tilings. That means that no matter how you put them together, if you put them together following the rules he created, the tiling you got would always be one where you can't find the big piece and like shift. You have to use like a procedural way of generating them. You know, you have to follow a set of rules. But it takes like 20,000 tiles, and if you take these 20,000 tiles and follow the rules, you can do that. Well, later in the 70s, Roger Penrose actually discovered that you can actually create a tiling using just 2. He actually started off with 6, and he got down to just 2. And he found 2 different ways of doing that. So the first one here, this is called P2. It's the second Penrose tiling. The first one was the one with like 6 tiles. So I'm not going to worry too much, but he got it down to 2. And so we call this the kites and the darts. So kite, you know, this is like a kite shape. This looks like a dart. And that's actually this top one. So this one up here is actually P2, and that's what it would look like. So it basically has a way of like how you connect these. There's little like tick marks you put on them, and it says, okay, the tick marks have to match. And so there's a way you can assemble it, and you build this whole thing. They kind of colored it with the different colors. You can see the kites are red, and the darts are yellow, and they colored it. And this tiling, no matter how big a piece you take as big a piece as you want. If you try and just translate it, like shift it up, down, left, right, you'll never like get the same picture again. There's just enough variation. You can see like there are some shapes that look similar, but there's lots of little variations in there, and there's so much variation, you can't just take a copy of this, slide it over, and cover itself. And Penrose was able to prove that. He also found this shape. This one just uses two rhombi. So there's kind of a skinny rhombi and a fat rhombi. Rhombi just means like they're like squares where all sides are the same, but their angles are not 90. So they're two sides, almost squares, but not quite, so 90-degree angles. And here you kind of the fat one blue and the skinny one like a light blue. And that's P3. That's the third tiling you found. And so since the 70s, these have been the two options. If you want to tile aperiodically with the fewest number of tiles, you would use either the kites and darts or the two rhombi. Well, actually, while I was getting ready these notes, I actually, when I first did my notes 10 years ago, those were the only ways to do it. But just a couple of years ago, in 2023, an amateur mathematician, not even a professional, not someone that like works as a, at a college his whole life, or an amateur mathematician, someone who just liked to study math on top of his day job. He's retired, but so he can focus a bit more on the math. He actually came up with a tiling, an aperiodic tiling, using just one shape. It's a pretty big deal because we've been looking, the 60s, Berger came up with the first periodic tiling. So since the 60s, we've been trying to find out, is there a way to do it with just one? So it's been 60 years, and he finally found one. So 60 years of mathematicians looking at this problem going, is there a way to do it with just one piece? And David Smith, an amateur mathematician, discovered a single tile that is aperiodic. So you use this one tile. If you tile the plane, it will only tile aperiodically, which means you can't just grab a chunk and transfer. Even though it's just one tile, you can't take the one tile, because here he's doing like rotations and stuff to get all these different connections and stuff. And you can't take a big enough piece of this and like translate it and have it copy over top. So yeah, this is a news article from just 2 years ago where it talks about, hey, he discovered this. This is a big deal. He's on Wikipedia as the person that discovered this. He published papers with other mathematicians who verified that he's correct, that this piece works. This one's called the hat. He actually did develop another one called the Spectre, so it does it even better, because the hat, in order to do the hat, you end up actually having to like flip the piece over, so you can almost think of it as two pieces, because you have the hat and then the back of the hat, so you have to like use like two different sides. The Spectre he actually designed where it only works if you don't flip it over, so it actually only has one way to do it. That was kind of a big deal. So both his discovery of the hat and the Spectre were really big deals, because they showed that you can create this aperiodic tiling where there's no repetition. You can't just take the big chunk and slide it around, and you can tile the whole thing. So it's kind of cool that we're getting to look at. So this is like current mathematics. This is something people are studying and figuring out right now for us. So, but yeah, that's it for us. So big thing I saw, you'll do homework problems where you have to do those translations, rotations, and reflections. Be ready to do those for the homework. You should understand a bit about the tilings, the difference between the regular polygons and the irregular polygons, that kind of stuff. So you'll see a little bit on the homework. It's not a super long section, but definitely it's a pretty interesting section. Hopefully you enjoyed that. I'll see you in the next one.